Well, in the previous lecture, we have already discussed these two approaches. One was the bisection, which was very easy, and there was absolutely not much, methodology which we need to discuss. It is just once you know that there is a root in between, then you keep on, dividing that interval into two pieces and see where it lies, and finally you will converge to that root without any problem. The fixed pivot iteration method, so there were several possibilities how we rewrite this fx is equal to 0 to x is equal to gx, and once we have written this x is equal to gx, you can set up the iterations, but we had only that sufficient condition that this g prime x should be less than 1 in that interval, and then the convergence is guaranteed. Today we will discuss about the Newton-Raphson method and the secant method. Both are related, and I am very much hopeful we will be able to finish within this lecture everything related to this chapter. So next week we will start with interpolation. We will finish in 2 lectures, and then tomorrow we will finish that interpolation. In the next week, maybe we will take 1 lecture for numerical integration. So the Newton-Raphson, the idea is also very simple. So for instance, this is the root, and we have this function here, this y is equal to fx. So what we do, we start with some initial guess of the root. So we have taken, for instance, here the initial guess, though our exact root is somewhere there. So we have started with again some initial guess. At this point, this is the value of the function, so fx0, and you draw a tangent at this point here at x0, fx0. So this point is exactly x0 fx0. So at this point you draw a tangent, and the tangent will meet this x-axis on this point, which is exactly the x1 in this Newton-Raphson method. So this is exactly based on the tangent here, and again this x1 you try to find that point here on y is equal to fx, again draw the tangent, and so on. We'll keep on doing this. So let's first compute that what is exactly this x1. What is this
Can you
x1?
please repeat? I was not like I was the connection was not proper. The last
So
part.
we
Can you
have
repeat?
so we have the root here of this function, the given function. What we do, we take initial guess somewhere, possibly closer to this, as the convergence would be faster. So you have that x naught somewhere, then you have this point where it meets, the vertical line meets to the y is equal to fx line. So that point is x naught fx naught, and there you draw a tangent. At this point you draw a tangent, and that tangent will meet the x-axis here, and that will be our next approximation, x1 to the root. So this is your x1, and now you consider this triangle here. So just to know what is that x1, just consider this triangle. So in this triangle here, the f prime x naught, the tangent at this x naught point, would be this distance here, which is nothing but fx naught, right, divided by this x minus x naught minus x1. This divided by this is equal to the tangent at x naught point. That is the simple formula we know of the tangent. So this f prime x naught is equal to fx naught over x naught minus x1, and from here you compute what is that x1. So this x1 will come as x naught minus fx naught over f prime x naught. This is the formula of the Newton-Raphson method, which we can generalize now. This is our first step, where from you will start from x naught and then you will get x1. But then again we'll proceed in the similar fashion. So we have x1, then you have here fx1, and then again you will draw a tangent, which tangent will meet here, and again this triangle you will compute your x2. So the x2 will be x1 minus fx1 divided by f prime x1. So we have this x2, then we have x3, then we have x4. K plus 1th step will give us xk plus 1 is equal to xk and minus this fxk divided by f prime. So this is the iteration scheme which is called Newton-Raphson method, the most popular one among all these. And obviously this is very much used even today. So here we can, and there are some reasons which
One
we
doubt,
also discuss.
sir.
Yeah. Hmm.
It might it happen like suppose the root of fx is at x right in there, and so we have started an initial guess to the right of the root. So can it happen that that as we are conducting the Newton-Raphson method, we are finding the root sequentially? Can it happen that can go to the, like, one of the
Yes,
guesses
yes.
may go to the
To the
other
other
side of
side you
the?
mean.
Yes, sir. Can
Yeah.
it happen?
Yes, yes, yes. It can happen. It can go to the other side, and then again this you will go. So again, we will have that sufficient condition for the convergence also. So, but let's proceed. There are many issues also. It is not just that you have the formula and then you apply.
Excuse me, sir.
Yeah.
So, sir, if the concavity of curve is downward, then will it converge, sir?
No, we don't have the condition, the sufficient condition for the concavity. So let's just continue and you will realize only the first derivative condition is enough. Hmm? So here what we have, the xk, this is just the alternative formulation. So in a line we will finish it. So this is obviously the geometrical interpretation, geometrical way of deriving this iteration scheme. Another way could be that you have this equation fx equal to 0 which you are solving, and then fx k be an approximation to the solution. Yeah, let's say xk be an approximation to the solution, and delta x be an increment in this xk, so that xk plus delta x is an exact root. This is what our initial, kind of setup to have that Newton-Raphson method. So xk is some initial, some at kth approximation. So usually you start from x0, but to generalize it, we have taken that xk is the approximation at some kth or approximation, or at some point you have taken, but usually from the initial guess itself. So just for the derivation, we have taken this k number there. So xk with the approximation, and we take that xk plus delta x. So we add some or subtract something delta x, so that this is an exact root. Now the question is, what is the delta x? How to get the delta x? What is the relation of xk and then delta x? So here we have this equation which will satisfy, of course, because fxk plus delta x is 0 as per our assumption. Xk was some approximation. Then we say that if we add delta x or subtract delta x from this xk, it becomes the exact root. That means fxk plus delta x should satisfy this equation. And now you take the Taylor approximation here. So once you open this expand this using Taylor approximation, you will get fxk plus delta x f prime 1 over 2 delta x square f double prime xk and so on, and set equal to 0. Naturally, we have so many terms here, infinitely many terms, so we cannot formulate anything if you consider those infinitely many terms. So just an approximation that though delta x was, xk plus delta x was satisfying the given equation exactly, that means this equation now here, but we neglect this higher order terms and so on, then naturally this delta xk will not be what we have started with, that this is the exact root xk plus delta x, but this will somehow give you some kind of approximation. That is the idea, that you have not taken the higher order term, you have taken order up to linear, and then you have neglecting this second order and the higher order terms. What we get this, that fxk plus delta x f prime xk is approximately equal to 0, right? So from here, what did we get? We get an approximation of this delta x which is equal to fxk minus this fx k over f prime x, right? So we got the approximation of the delta x. We did not get exact value of delta x, of course, that is not possible. We get this, that is nice, because you will get exact value of the root. So that means our iteration scheme becomes that you have the xk plus 1. When you have xk value, you will get xk plus 1 value, just xk and plus this delta x. This is what we have started with. So the delta x is nothing but minus fxk over f prime xk, and then k are these iterations. Did you get this derivation?
Yes, sir.
Yeah, so it's
Yes,
another
sir.
way of looking at it. Yeah, another way of looking at it, that you assume that xk plus delta x is the root, and then you have done the Taylor expansion, and then of course to handle this you neglected all higher order terms, and then you got the approximation of delta x, and that means the new value you can get xk minus fxk over this one. Yeah, so that's a fair, I think fair enough. Well, so just you recall from the fixed point iteration method where fxk was written as x is equal to gx, right? You still remember. And then we had set up the scheme as xk plus 1 is equal to gxk. There is a close relation with the fixed point iteration method. That's what I am repeating that here. So, and you also remember that the convergence of the fixed pivot method, the fixed point iteration method, was based on this condition that g prime should be strictly less than 1. And if we take our gxk, I mean gx here, if we take our gx as x minus fx over f prime x, if we take gx as x minus fx over f prime x, so basically we have this Newton-Raphson method, which is given here. It is a special case of fixed pivot iteration method, right? The fixed pivot iteration method, if you write, because there was several possibility, yeah, the given fx equal to 0, we had several possibility how we write from here to this gx, x is equal to gx. So what we have done, and is a special case, that x is equal to, we have written x minus this fx over f prime x. We have written this. See, this equation is exactly this equation fx equal to 0, because this x gets cancelled, and then you have this fx equal to 0. So you are getting fx equal to 0. It's the same thing. So we have rewritten fx equal to 0 in this form, x is equal to x minus fx over f prime x. That means your gx is just x minus fx over f prime x. So it's a special case, the same scheme. It is a fixed pivot scheme where the structure of the gx is fixed as x minus fx over f prime x. Is that clear? This step is clear to all of you?
So if f dash x k is equal to 0 sometimes, then will it hold?
This will not hold. This does not make any sense. The whole iteration method does not make any sense. Yeah. If f prime at some xk becomes 0, then it does not make any sense, right? It will blow up and it will fail
Yes,
immediately.
sir.
Correct? So we'll discuss those cases. I have some, in fact, numerical examples also where you will see many observations. Well, so what we learned here, that this Newton-Raphson method, this is a special case of fixed pivot method, a special case. This is a special case, nothing else. It is a special case of fixed point iteration method, nothing else. So we did not learn much so far. It is another fixed pivot method, fixed point iteration method, where gx has this special form x minus fx over f prime x. And whatever problem fx is given, you can immediately set up your gx, and then you have this actually fixed point iteration method, which is called Newton-Raphson method. They were developed differently, but finally you see that these are actually same. So now we come to the convergence of this fixed. See, we have already seen the convergence of the fixed point iteration method, isn't it? Fixed
Yes,
point
sir.
iteration method convergence we have seen already. Now we'll go
Yes.
into more detail. So to the convergence of the Newton-Raphson method, let me just finish this and situation will be clear to you that here we have that necessary condition which we have there, that G prime is less than 1. This is automatically there here in this case Newton-Raphson method. So the convergence is guaranteed. And other than few cases, for instance, once one of you has mentioned just now that G prime X becomes 0, then naturally there is no point of convergence because the method will break down at that stage itself. So there are some exceptions, but otherwise the convergence is guaranteed, as you will see. And in fact, why this is more popular, the Newton-Raphson method, I will also clarify in these steps only. But we'll go a little faster because we have to also finish this today. So xk plus 1 gxk, that is our Newton-Raphson method, right? Where gxk is that special form xk minus fxk over f prime xk. Let's see that s is the exact root. Yeah, because for the convergence we need to get that error xk minus x. So this s, let's assume that this is the exact root of this fx is equal to 0. That means s satisfies this s is equal to gs. Now this is your gx, as we know already, and g prime. What is g prime? Can you compute that g prime? Yes, easily. So you have 1 here, and then this quotient rule, then you will get this a derivative of the fx over f prime x. So we have the derivative g prime x. What will be g prime at s? G prime, the derivative of the g at this s where the root lies. What will be that value?
So fs f double dash s divided by f dash s.
Yeah, so here you take this one, f prime x, this will get cancelled, and then you will get this one, right? And this is equal to, any further simplification?
0.
Yes, because fs is 0 there, right?
Yes, sir.
So we have this fs equal to 0. As fs equal to 0, we have g prime s equal to 0. So one thing I can make a short note here itself, that g prime at s is the root actually, right, is 0. Correct? Naturally, we assume all continuity differentiability assumptions. So if g prime at s is equal to 0, if we have taken any approximation within, close proximity of this root, then naturally g prime s will be less than 0 because of continuity. It will not just, go up. It will continuously move from 0 to some other value. So there you will always find an interval along this s, that if you take a initial guess or approximation here within this interval, definitely that g prime s is going to be less than 1. Is that clear? G prime s is exactly 0. So always along this s you will get an interval where the derivative will be less than 1. So in this whole interval, g prime will be less than, strictly less than 1, right? Is that clear?
So can you please explain this part? I'm not understand.
Okay.
Yes, sir. Please
So
explain again.
what we have realized, this is okay, that g prime s is equal to 0 we got.
Yes, sir.
S
Yes.
is exact root. Fine. So we have
Yes, sir.
somewhere this root s. What I want to say, that along this s we will get an interval here where g prime s will be 0. Is that is less than 1? Will we get always this root if this g prime is continuous?
Yes, sir. However, from the
Yes, sir.
interval, we will get an interval.
Yeah, because g prime is continuous, then definitely you will get an interval, because that cannot happen that as you leave this s and then the function will have value 100. That cannot happen, right?
Yes, sir. Got
It
it.
will continuously move.
Yes.
So always around this S there will be an interval where G prime S will be 0. So I'm coming to that sufficient condition of the fixed pivot method, fixed point iteration method. So if that route which you have, if that approximation which you have started is from this interval along this S, then definitely your iteration scheme will converge. Is that clear? Because that sufficient condition is satisfied. So my point is, now we are not bothered about that, that sufficient condition for the convergence. We will go further. We will have some more results, more information, in fact, in this particular case. So let's proceed. We expand this gxk around this S in this scheme. That means xk plus 1 is equal to gs. So gxk, I'm expanding this gxk. gs plus g prime s xk minus s half g double prime at some xi xk minus s. So Taylor series expansion, you have to remember that. Always we use several times. So xk plus 1, here the Taylor series expansion of this gxk. Everybody is clear about this?
Yes.
Yes, sir.
Yes, sir.
Yeah. So gs, g prime s, this, and then we stop here. We are not going to have infinitely many terms. So we stop here. That is the remainder term. If you remember there, where this xi is not exactly known, but it is somewhere in this interval. Good. So fine, we have this. Our iteration scheme is just, this is the expansion where the equality happens. So we are not doing any approximation further. Xk plus 1 is equal to this one. Equal to this one. Well, so xk plus 1 minus this gs is s, right? As per our definition, s is gs, right? So this is s. That means we have xk plus 1 minus s. You know g prime s?
0.
Is 0. Then you have half of this term. Fine. So this is ek plus 1, right? The error at k plus 1th iteration is equal to this one, and here you have the error at the previous iteration, ek square. So what is interesting here, that each successive term, error term, is proportional to the square of the previous error. And that's a good news here, that error in each step will have the square of the previous one. So just imagine that at some stage you have error 0.01. Then in the next step your error will be 0.01 whole square, 0.0001. Correct?
Yes, sir.
Which one is better, if we have here a linear term or quadratic term?
So, but
So
if the error is
quadratic
greater
term.
than 1, it will blow up.
Yeah.
In that case, it will not converge.
Yes, so we always talk about all convergences, not only here itself, that you have basically, when you prove this analytically, that the method converges, is usually by default that error is a small one. And then what happens? Yeah, so error is very small, then it should remain small and it should go to 0. That is the convergence. It is not like that having the error is very, you have 100 or more than that, and then you are talking about the convergence. That is not the case. So that is fine. Always we talk in the convergence that the method is convergent when you have an approximation which is in the close vicinity of your root, and then this analytical result says yes, it will converge. It will not go somewhere else, but it will converge. Yeah, all those issues numerically you will observe that yes, what exactly you said, there is no guarantee from here. If the error is bigger than 1, it may happen that in the next step it is even bigger. Correct? So those things will come, but the convergence says that it is guaranteed as you have, if you have that approximation in the vicinity of the of the exact root. So I will mention also that in the remark here in a minute. So hence the Newton-Raphson method converges quadratically. That is a very good news actually. The Newton-Raphson method converges quadratically. This is exactly the meaning of this statement. When the error is the quadratic to the previous error, then we call that method converges quadratically. What is the difference between a general fixed point iteration method and this one? In a fixed point iteration method, that G prime S may not be 0. G prime S may not be 0, and that is the advantage we are getting here for this higher order, where the error gets in square, because in otherwise this will be a linear term, right? If this G prime S is not 0, that your error will just reduce linearly, not quadratically. So here, that's the reason that Newton-Raphson method is a special is a special fixed point iteration method. And the special about this is this quadratic error, that it converges quadratically. Well, let me just finish. Yeah. Your voice is very much on and off, so not clear. Yes, again.
Hello.
Can you repeat?
Sir, EK plus 1 is proportional to previous error term, a square of previous error term, right, sir?
Yeah. EK is.
And are you saying that it converges quadratically?
Yeah. Yeah. That's a theoretical convergence, that if you have the approximation in the vicinity, then this guarantees that it will go to the root.
I am asking why are it Newton geometrically? I don't understand this part.
Sorry, I could not get you. Your voice is completely on and off.
Why are you saying that?
No, not at all. I'm not hearing anything now.
Type in chat box.
Okay, so let's just complete this. Maybe your question will be answered towards the end of the lecture, right? Okay, so in general, in the fixed point iteration method, G prime X is not equal to 0, and hence the method converges linearly. So your fixed point method converges linearly. That bisection method converges linearly. But this method, the Newton-Raphson method, converges quadratically, and that's a big advantage.
So, how can
Yeah.
we say it converges linearly in that case? Because there will be the remainder term in that case also. Like there will be half G double dash.
Initially it is
then-
dominant.
This is the error equation, right? This is your error equation.
Yes.
Where you have, let's say, ek plus 1 is equal to, the first term is G prime S ek plus half G prime xi and ek square, right? This is your error equation. This G prime S, we don't know. It's not clear that it is 0 always there. But in this way which we have constructed our G prime S is 0.
Yes.
In those, G prime S will not be 0. In general, G prime S is not 0.
Sir, I typed my question in chat box. You can.
Okay. So that is clear here.
Yes, sir. Like the linear term will be larger in that case, so it will be dominant. So
Yes.
that's why we're
Yes.
considering.
Absolutely. Absolutely.
Excuse me, sir.
Yeah, quadratically means itself that is a square of the previous term. So that is exactly the meaning. Your question is, why are we saying that converges quadratically even though it is proportional to a square? So yes, that is the meaning, that it is proportional to the square of the previous term. That is exactly the quadratic term we are using. If it is proportional to the linear, then we say it is linear. Yeah. Yes,
So now
exactly.
I
We
Excuse
are
me,
saying
sir.
quadratically because it is proportional to the square term. Exactly. Fine. Quadratic is square.
Sir,
Yeah.
sir, if we have inflection point near root, then
Loud,
we might
loud,
have
loud,
a
loud,
problem.
loud, loud.
Sir, if we have an inflection point near our root, then we
Huh?
might get an problem also.
I'm coming to those cases. Just let me finish. Yeah. So I have few special cases where I will discuss those problems. That what are the problems of this method? Yeah. As I mentioned beginning also there are problems. Hmm? Okay. So this is okay. Up to here the quadratic point.
Yes, sir.
Okay. So what we have in the case of the fixed pivot iteration method, this is okay linearly. Moreover, the size of the G prime X matters and it has to be less than 1 for convergence. That is what we have discussed in fixed point iteration method. In this case, G prime S is equal to 0. Therefore, the convergence is guaranteed for X not sufficiently close to S. Yeah, this is I think I have discussed on previous slide. That if your X naught is sufficiently close to this S, then the convergence is guaranteed because you will be in the interval where G prime S is less than 1. As discussed in the case of Newton's, the method converges quadratically for X naught sufficiently close to S. Again, that point which some of you has mentioned that it may happen that this is greater than, the error is greater than 1, naturally then we cannot say anything. So but the theoretical result always about the convergence lies on such a concept that you will not consider those cases when that is far away from that initial guess. So here the convergence is quadratic when x0 is sufficient close to S. Let's go to straight example here and then those special cases we will discuss. So perform 4 iterations of the Newton-Raphson method to find the smallest positive root of this equation, for instance. So you take initial guess as 0.5. I mean, you can take anything. The root is between 0 and 1. So you can take anything. So we have taken here 0.5. F prime is this. F your iteration scheme is here. And then you just apply this scheme to get the next values. So start with this x 0.5. That next value you will get x1 is equal to 0.176470588. There are two terminologies usually used. Yeah, please pay attention. Once in some we can say that okay, approximate the values to 4 decimal places or round off to 4 decimal places. So round off, if I say round off, what do you mean by round off? What is the round off to 4 decimal places? What will be the value? 4 decimal places.
0.165, 1765.
165. If I say truncate, chop off, yeah, truncate to 4 decimal
0.1764.
1764. Yeah, clear. So that's the two terminologies we usually use. One is the round off, one is the trunk. So if we want to truncate, for instance, then the value of x1 is 1764. Then you can go using this value to the next one or use the complete one, whatever. There will be slight difference. So here x2 will be 0.21, then so on. Then you have x3 0.201. So you can see that kind of convergence, right? 201 is matching, 3 digits are matching. Then we have x4 2016 up to 4, it is 4, in fact it's 5 6. See how fast this converges. Once you are here, the next you see you are matching up to, my goodness, you are matching up to this one, correct?
Yes, sir.
So 1 2 3 4 5 6 7 8 9, up to 9 digit you are matching with the root actually, because the convergence, yes, you can see easily that converge. It will, if you go for x5 you will see hardly any change up to, I don't know, 10 12 digits. So this is, if you could have used the earlier method, maybe we have used for the same problem. Was that problem same in the earlier case? Do you remember our earlier test cases for the bisection and that iterative method and this fixed point iteration method? If this was the same example, you check again. So there we had to go with 15, 16 iterations to get such an accurate value. But here with 4 iteration, you are getting a highly accurate value. The reason is the superiority of this Newton-Raphson method, the quadratic convergence. That is the reason here. Apply Newton-Raphson method to determine a root of this equation cos x minus x e power x equal to 0 such that the fx star means this is the accuracy, right? The fx should be 0, but we are talking about that fx star should be less than 10 raised to power 8 minus 8. And initial guess you start with 1. So everyone can follow this, of course. You have the scheme, you have this scheme xk minus this fxk, then f prime xk in the denominator, and then we need to apply. So the k will be for iteration, then you have xk, the value, and we need to compute fxk to just see whether how far we are from the actual root, because fxk should be very close to 0. So in the 0 iteration, you start with 1. The value of fxk is this one. In the next iteration, you go. So you have xk will be coming 0.653, and then the check you can check fxk. This is still very large. Here we have not fixed the iterations, right? We have fixed the error. That error should be less than this. Error should be less than this. So then we go with the third step, and the value of x is this. This is the fxk. Go to the third step, 0.5179. As you can see, okay, your value is getting smaller. This. Go to the fourth root, fourth iteration, 5.9 10 raised to power minus 8. So we cannot stop here also, because your fxk should be less than 10 power minus 8, right? 10 power minus 8. So we go one step more, and then we have 0.5178, and here the value is 8.8 10 raised to power minus 16. So naturally we should not go more here. We need to go for only fifth iteration. The approximate root is 0.5178. Clear?
Yes, sir.
Yes, sir.
Okay. So there is a secant method. Just on one slide I will explain, because this is the same as Newton-Raphson method, and then we will go, as I mentioned, those special cases where there are problems with these methods. So the Newton method is very powerful, no doubt about it. There is a disadvantage. The one disadvantage is the evaluation of f prime, because every step you have to evaluate that f prime, right, at some point, which may be computationally very expensive. Because why I'm talking about very expensive, in many problems you cannot get some analytical expression indeed for that derivative term. So then you have to have some numerical approximation to those derivative terms in each step, and that makes it computationally very difficult. And the second point is that getting that approximation of that root of that derivative is also not easy. That is difficult. So that is the drawback here. The secant method is a variant of the Newton method, where this fxk is replaced by the following differences. So this fxk, the derivative, we have replaced by this fxk minus 1 over xk minus 1. You remember that the definition of the derivative is something like this, the constant, and then you say that the limit xk goes to xk minus 1, right?
Yes, sir.
This is the definition of the
Yes,
limit.
sir.
So definition of the derivative. So naturally, we are not considering that limiting case because that's what we want to get rid with this derivative term. So instead of doing that, we will use this quotient values. That instead of that f prime x, we will use this fxk minus fxk minus 1 over xk minus 1. So that's the method now, which
Then
is
we have to take
secant.
into consideration the previous term and the previous to
Excuse me,
previous
sir.
term.
Yeah, exactly. So not only the previous term, but previous two terms are being considered here to the for the evaluation of the next term. So for instance, x0 you need also x1. In the Newton-Raphson you need x0 and then you move forward. Here you need x0, you need x1 also first. So you compute whatever way you can get. You have another fixed p1 method, fixed point iteration method. You have the first one, the bisection method. Use those methods whatever ways. You compute first x0 and x1. And once you have these two, you can set up this secant method and you can get the result, the
Excuse
approximation.
me, sir.
Yeah.
Hello. Sir, derivative represent the tangent of function, right? Then why it is
Yeah.
called secant method? Why not tangent method?
Secant is, I don't know why secant, not the tangent one. See, this is not the tangent. Yeah, the
Sir,
tangent is used in Newton-Raphson method. Yeah.
No, sir. I
It's
am
a
saying that
equation of secant
derivative
actually.
represent and
Yeah. So the tangent is used
And
exactly in the
two
secant method, not here. There we use the tangent to get this approximation, but here we are not using tangent. Yeah. We as using this secant. Yeah.
Excuse me, sir.
Mm-hmm.
Sir, here k is should start from 1 now.
Yeah,
I
k
yes,
will
is
sir.
start.
x0.
Yes, k will start from 1. So you will get the first approximation x2. Huh? You will get the first approximation x2, not x1. Fine?
So means we have to take two initial guesses here.
Yeah, this is what I said. You
Yes,
have to
sir.
take two initial guesses. So this method is not in your syllabus. So for the exam point of view, you can leave this one. This is just I have mentioned that this is also another way of looking at it when there is a difficulty in
Excuse me,
evaluating
sir.
that f prime. Yeah.
Sir, in this case also the error should be converging at in a quadratic time. I
It is
mean, with
not, you cannot prove the quadratic convergence here.
I thought the operation. I mean, the basic format was similar to the Newton-Raphson. So I also
It
thought
is
that in this case
similar,
also.
but there the when you prove, you have to prove, right? So G prime S was
Yes,
0
sir.
there, right?
Yes, sir.
So that you cannot do here. But what is observed in practice, it is quite good. It is close to like Newton-Raphson method. Yeah. It is not quadratic exactly. It is slightly less than quadratic, but close to. Definitely much better than the linear one or the other two methods we have discussed. But you cannot prove quadratic convergence exactly out of this secant method. Yeah. So theoretically, you cannot prove that it is quadratic, but it is close actually, that numerically one can check that. Now I will talk something on this Newton-Raphson method, the pitfalls, that where the problem exactly happens. One which was very clear, the
Hello,
method
sir.
fails. Yeah. Yes.
Sir, can you explain why we can't put quadratic equation?
Hmm? Sorry.
So I was talking about quadratic convergence, not equation, I think.
You are confused with the quadratic convergence.
So he
Right?
was asking why we
To
cannot
prove the
put.
convergence, you have used that derivative term, na, which was 0 there. That's what you got second term. True? Here that derivative itself, you are just approximating by something. So how will we prove that quadratic convergence here? So in practice, this is observed that it is close to order 2. It is close to quadratic convergence, but not quadratic. Fine?
Sir, actually there was an electricity loss, so I didn't hear anything. I
Okay.
joined mobile phone now.
Yeah. So it is not quadratic, but it is close to quadratic. Much better than linear cases. Still, when you use that quotient term instead of derivative. That is the idea. So that, as I said, the secant method is not in your syllabus. Yeah, this is not in your syllabus. So you leave with this one. The Newton-Raphson method, so there are some pitfalls. The first one is that the method fails if f prime becomes 0 at any approximation xk. So when you started with something, it is going fine, but at some point this f prime at xk becomes 0. And as soon as this becomes 0, you cannot move further. So that is the one pitfall which is clear from the formula itself, that once this is equal to 0, so this should be always not equal to 0 during those iterations, then only you can move further. Cycling behavior leads to complete failure of the method. What cycling behavior I am talking about? There are some situations that you start with this x0. Yeah, you start with this x0, you have the tangent, you got x1, and then this again you get x0. So what will happen in this situation? You will have x0, x1, x0, x1, x0, x1, and so on. Nothing else will happen. So it will not move further, not towards any route, but it will just move between x0 and x1. That can also happen, and that is another failure. Another failure which you just consider this
We can
example.
change our initial guess. Hello, sir.
Yeah.
Sir, if that is the case, then we can change our initial guess.
Yes, naturally. You shift your guess, then you can get rid of this cyclic behavior. So once you observe that, yes, that is the
Sir,
first thing we should do. We should deviate from the initial guess a bit.
but sir, it is difficult now because after we guess any guess after that maxima will repeat, I think, or it will always give wrong thing.
Yeah, there are many. You will see just even more
Is it
serious
going to
issues.
occur if the graph, like if the plot has a slope 0 in between, only then it is going to happen, right?
Yeah, but if you change a little bit, that is not the slope is responsible for this behavior. If you change that, then you will get rid of this. है ना? So this is a very special situation. It is not like I'm saying that it will happen in your all problems. This is a very, very, very special problem where you exactly chosen that x naught in such a way that this is happening. Yeah. So this is a rare situation which can easily you can deal by deviating a bit from the initial condition.
Okay.
Yeah, but this is not just the initial condition, that can happen somewhere in between also, right? This is just an example that you start with x0 and then x1. So you have xk and then xk plus 1 happen this one. So once you see the cyclic behavior, you have to change. You have to divert from that point somehow. You will not see frequently. I never have observed such a issue, but this can happen. Very special examples you have to form, and then you will observe these also. So for instance, here you have this fxk cubic polynomial. Actual roots are 3, 5, and 15. What is happening here? Just let me point out that those things can happen. This is what I want to say. You started with initial guess 4. Yeah. What will you expect? That either you will go to 3 or you will go to 5. But what is happening? You are immediately going to 15. So some surprise results may come, that you are expecting that you are having a root somewhere 3, then you start with closer value which is 4, and then you realize, oh, you got to another root, so it is converging to a very different root. Same thing here. Now you change 4.2, for you have slightly perturbed this value, then you are getting to 5. And then, for instance, if you take 3.9, then you are getting to 3. So there are several, I mean, there is no unique way of defining that you take this initial guess and you will converge to that particular root. For instance, here also one more example of similar root situation. Your roots are 1, 3 and 9 minus 98. You start with a initial guess 2. What you will observe out of these iterations, you are converging to minus 98 immediately. Minus 98, and that is this root. You divert a bit, 2.4, you are converging to this 3. 3.9 if you take, which is close to 3, right? 3.9 is close to 3, but you are converging to 1. So there is no guarantee that you start with a initial guess which is closer to some root and then you expect that this will converge to that root. It may converge to some other root. Usually this happens that you start closer to that root, it goes to that root, but that is no guarantee. It can go to anything else. So the point is that the Newton-Raphson method is a very nice approach. It's a quadratic convergence and alternate where you have difficulty finding this derivative. You can also use the secant approximation of this, very close approximation. And that's actually all for this lecture. Now if you have a question, we can take few questions now, and otherwise yeah.
Sir, in the last example, we saw that 3.9 gives us the